Okay, guys, here we go. Been a long weekend. Well, not too long. It comes just fast. We are in week 10. We got 6 weeks left till finals week. Oh my goodness gracious. Plus we got Thanksgiving in there. We are just looking, guys, looking. Next Friday is exam number 3. Next Friday is exam number 3 on module 3. We've got some warm-up problems. The first one says plot the following points on the polar plane. The second one says solve for theta where 0 is less than or equal to theta is less than or equal to pi. A says cosine of theta equals -1. B says sine of 4 theta equals 0. We want to warm our brains up. Get us going here to start us off for this beautiful, lovely, cold, 32-degree morning. Were you cold this morning? Ty walked in with shorts and a t-shirt, and he's like, dang, it's cold outside. Tyler Orban? You have Tyler Orban? You know him? Yeah. He's very by me. Is it 51 now? Oh, that's good. It was cold this morning. It was nasty cold this morning. All right, guys, we got some points. We're plotting polar points, and we're looking for thetas. Okay, I'm going to wander. Make sure you guys are warming your brains up here. Remember, polar paper consists of a pole, right? It's a pole, and then it's a series of circles that radiate out from that pole. 1, 2, 3, 4. They should be equal concentric. They're not when I'm drawing them, but they will be when you draw them or when you use polar paper, right? They'll be a lot neater. One more thing to remind ourselves, every polar point is not written X and Y. Instead, what's the coordinates? It's what and what? What are my coordinates in the polar plane, polar realm? There. R and theta, thank you. R and theta. Where R is the distance from the pole, right? And theta is measured from the positive x-axis, which we call the polar axis. So theta always gets measured from the positive x-axis in the counterclockwise direction, just like on a unit circle if it's a positive value, right? You guys got 3 points plotted, yeah? Are you still working? All right, I'm going to record. I'll send it to him. But you guys are taking notes. You got him? Do you see Tim? Is he your roommate? Whose roommate is he? Does he know? You guys know Tim? Okay. Yeah, if you can, Ben, take some notes. Vincent, you guys see Vincent? Get some notes for him. Eli, he's always, okay. Yep. Okay, I think everybody else is here. Here we go. Oh, yeah, and Shane asked for notes. I'm going to send him a video, but if you guys know Shane, he's in my 8 a.m. class. If you guys know him, you can share notes with him, too. Here we go, guys. 2, 11 pi over 6. Give me a quadrant. Ethan, what quadrant am I in? Fourth quadrant. 11 pi over 6 is approximately 300, not approximately, is equal to 330 degrees. So if I want to go 2 units out to 330 degrees or 11 pi over 6 radians, I'm going to be down here in quadrant 4. Everybody good? Cool. All right, Zach, tell me, in what quadrant is 5 comma negative 3 pi over 4? Oh, this Zach. Yep, I'll get you this Zach. We'll do the other Zach on the next one. It's in quadrant to start with? Absolutely. So negative 3 pi over 4 is an angle down here, right? Negative 3 pi over 4 is the angle down here when I draw the negative angle. And then I have 5 units out. 1, 2, 3, 4, 5. And so I am down here. Is everybody down here? Quadrant 3. All right, my other Zach. Okay, Zach W.
I said quadrant 3.
Quadrant 3 as well. Why is that? Can you explain?
I saw pi over 3, and then since it was negative 3, it'd be on the other side.
So pi over 3 is this direction, 60 degrees, but it goes all the way. And so if I want negative 3, that means I have to go, this is the positive side, this down here is the negative side, so negative 3 puts me down here in quadrant 3 as well, so that point should be down there. Does anybody have questions on how to plot those polar points? I didn't ask you, but could you do this? Could you convert this polar point, negative 3 comma pi over 3, into Cartesian coordinates? Could you do that? In other words, can you tell me the x value and y value associated to that point? So can you convert that into Cartesian coordinates? Or in other words, can you give me the x value and y value that is associated to that point? How would we do that? How would we do that? What do you think, James?
I was trying to do it the wrong way. Never mind. I would say we took the square root of each square, so that would take us to the
Oh, we could do stuff like that. We could figure that out and go back that way. Absolutely.
Wouldn't it just be cosine of 4 pi over 3 and then sine of 4 pi over 3?
It almost.
Or would it be just pi over 3?
That would give you the cosine and sine of those. That would give you, Allie, the points on the unit circle.
Oh.
Are you with me? So then you'd have to multiply by the radius, right? Yes. So, how could we do it? I love your brain. Absolutely. You could find the point on the unit circle, cosine or sine, of associated with pi over negative 4 pi over 3. Yes, 4 pi over 3. Nope, 5 pi over 3. I think you said. Hang on, Tina, get this all. 4 pi over 3, sorry, 4 pi over 3, yep. So we would find the sine and cosine, but then multiply by 3. That'll get us those numbers. Or we could also use our conversion factors, which are the exact same thing that you're saying. What did we say x was equal to last time? Who remembers? Yeah, Gwen. X equals r cosine theta. And what else did we say about y? Y is equal to r sine theta. That is exactly what you just said, Allie. I love how you used your brain first. You said take the cosine and the sine, but then we have to expand off that unit circle and multiply by the radius. So if we have just x equals r cosine theta, that's exactly what we're doing. We are getting the radius and multiplying times the cosine value. So for this, we would take negative 3, and we could multiply that by the cosine of pi over 3. Or we could do your way, use 4 pi over 3, but then make sure you just multiply by positive 3 because you're down at that angle down there. You used a different representation for your point. But let's say I didn't do any thought process other than plug theta and r into x equals r cos theta, y equals r sine theta. That should give me my x value. Ooh, cosine of pi over 3. Anthony, do you remember cosine of pi over 3? What is cosine of pi over 3? 1 over 2, it is. 1/2. Absolutely. Absolutely. Logan, you got me sine of pi over 3? It's square root 3 over 2? Absolutely nice. And so your x value should be negative 3 over 2, or negative 1.5. And the y should be negative 3 square root 3 over 2. So the Cartesian coordinates for this point, it is located about negative 1.5 units out, if you drew your circles nice and neat. Very, very good. And negative 1.5 times, square root of 3 would give us. So that would be converting that into Cartesian coordinates. Good, good, good. Oh, man, our brains are getting warmed up. We're getting warmed up, which is going to give us time to answer these questions. Any answers on that? Anything you guys have to tell me about? Yeah, Allie.
For the first one, when you -1 equals theta?
You could do that, And what is theta then? What angles would give me that in between 0 and pi? Pardon? It is pi. The cosine of pi is -1. Hello, easy peasy, right? The cosine of pi is -1. Would you guys all agree that the cosine of pi is -1? How many of you guys got the sine of 4 theta? Did you? What did you get?
0 and pi.
Oh, I'll give you that. I'll definitely give you 0 and pi. Oh, undo. 0 and pi are 2 of those answers. Yes, they are. Absolutely. Because sine of 0 is 0, sine of 4 pi is 0. Absolutely. Oops, in fact, that's probably at the end, Because it can only be between 0 and pi. Ooh, there's some more in there. James.
Pi over 4?
Pi over 4. Why does pi over 4 work? Let's check it. Because the sine of 4 pi over 4 is just the sine of pi, and the sine of pi is 0. Very nice. How about else? Give me some more. This is called guess and check. Logan. 3 pi over 4. Absolutely. Because if you put 3 pi over 4 in there, you have the sine of 4 times 3 pi over 4. You have to do inside before you evaluate the sine. You always evaluate this inner part first. It's like having a parentheses, right? A hidden parentheses around that argument inside. 4 times 3 pi over 4 gives me 3 pi. Sine of 3 pi is 0. Hello, beautiful. There's one more, guys. Hey, Caitlin. Pi over 2. Absolutely. Pi over 2. Because the sine of 4 pi over 2 is just the sine of 2 pi, and that's just 0 as well. So there are actually multiple spaces where this is true, but it's hard to see that. How can you do it if you're not guessing and checking? I'm okay if you guys want to guess and check this. That's perfectly fine with me. How could we do it otherwise? I'll show you. Okay, and why is this important? Okay, the reason this is important is we're going to start looking at the curves of these things. And we are going to say, what's the area bounded, or what's the arc length of this curve? Or what is the tangent line when this curve hits the pole? Right? It's when your curve equals 0 is when it's crossing your pole. So there's a lot of instances when we want to be able to know when our curves are going through our pole. And so we want to be able to solve these equations. One way, and let's see if this makes sense to you guys. You might have seen this in a previous, but you guys don't. So here's one way. If you don't see it, obviously, here's one way to look at it, is to say what you're really asking is the question, for what values of t is the sine of t equal to 0? But instead of t, you just have something that's standing there for t. T is just your placeholder, right? And says 4 theta could be t, 2 theta could be t, 5 theta could be t. But for us, we have 4 theta is t, but this is the bigger question. At what values of t is the sine equal to 0? And we know that sine is 0. Looking at our unit circle, it's always here and here. So t could be 0, t could be pi, t could be 2 pi, t could be 3 pi. Are you with me? ... So t is always a value of pi to make this true. So that would mean then 4 theta would have to be 0. 4 theta would have to be pi. Do you see what I'm saying? So what that allows me to do is create this equation. So 4 theta has to be 0. 4 theta has to be pi. 4 theta has to be 2 pi. So if you like processes, keep going, then you could solve directly for theta. Theta is 0 divided by 4, which is 0. Theta is pi divided by 4. Theta is 2 pi divided by 4, which is pi over 2. Do you see what I'm saying? That could be how you get your angles that we did with guess and check if you wanted to. You would simply say whatever angle is in here will replace the t values for what I know is true in this equation. And so once you do that replacement, it becomes very easy to know what those angles are. So I am going to ask you, probably on your test, here's a rose curve. At what angles theta does that curve cross the pole? And you'd have to give me those angles for where it crosses the pole. Does that make sense to everybody? Makes sense. This doesn't make any sense to you yet because we haven't played with polar graphs, which is our next step. I think what makes math hard is that as a math teacher, I have so many connections going on. Like when I'm teaching and talking to you about sine 4 theta equals 0, I'm pulling up a picture of a thing going through this, and I'm understanding what I'm saying to you, but you're just seeing sine 4 theta equals 0. You're just seeing this equation. So what I'm hoping that by the end of today is you guys are able to start actually putting together pictures with equations in polar curves, okay? At least start to talk about them. All right, I got theta equals pi over 4. Let's talk polar curves. Instead of y equals x squared, or x squared plus y squared equals 4, let's talk about polar curves, which are always, our variables are what, 2 letters? Not x and y, r and theta. Okay, so let's start with just theta equals pi over 4. Desmos will not draw this or graph this, so I won't do this by hand to get started here. What is theta equals pi over 4? What does it look like? What is it describing? What is that a relationship about? Theta equals pi over 4. What does that tell me in words? It tells me the angle is always going to be pi over 4, no matter what the radius, right? So what do you think that's a graph of? What do you think that's a graph of? The angle is always pi over 4. Guesses? Remember, you are students, and students ask questions. That's what we do. We ask questions to learn. And we don't have to have the right answer, but we ask questions or we guess. Yeah?
Is that equivalent to like y equals x?
It is. It is actually the line y equals x. It is simply the line that goes through the angle pi over 4. Also happens to be the line theta equals 5 pi over 4, but it is a straight line. That is just the line right here. This is theta equal pi over 4. No matter what the r value, the theta value will always be pi over 4. What kind of symmetry do I have? So when you talk about symmetry in an xy plane, we talk about symmetric with the x-axis, with the y-axis, and all that, and the origin. Well, let's translate that into symmetry with polar curves. If you have a polar curve, there's 3 types of symmetry you get. The first type of symmetry is in the horizontal axis. Then you have symmetry in the vertical axis. And then we have symmetry in the origin, or we call it for our polar curves, the pole. Do you guys remember what symmetry in a horizontal axis looks like? What would that be? Let's describe it. So symmetry in the horizontal axis says that whatever happens above the axis also happens below the axis, right? That would be symmetry in the horizontal axis. Symmetry in the vertical axis would take the same point but go around this way, right? Would be horizontally symmetric. And what would it look like if I have a curve here and I want to be symmetric in the pole or the origin? What would it do? Can you describe for me, how do you get that? So symmetry in the pole occurs that if I was to go over a certain amount in the x direction and then up a certain amount in the y direction, I would do the same thing on the other side. I would go back in the A direction and down in the B direction. So if I went the same distance back in the A and down in the B, and I got another point on the curve, and that happened for every single point, that would give me some symmetry in the origin. Do you guys see what I'm saying about that? So it's a movement. So for every curve, if you go over in X and up in Y, if I go back in X and down in Y, and I have that for every single point on the curve, it gives me this symmetry in the pole, or the origin, so to speak. Okay? So guys, can you tell me, does this graph right here, theta equals pi over 4, have any symmetry? What do you think, Robert?
Around the pole.
It is symmetric about the pole. For every X movement and Y movement, I have a backwards movement and a down movement. Absolutely. So we would say that this particular graph has symmetry in the pole. Very nice. And any questions? So now, do you guys have, did you guys bring laptops with you, or iPads, or tablets or anything? Now is when we're going to pull them up, open up Desmos, because I'm going to give you 5 new polar curves. Polar curves are curves that have r equals a function of theta, something involving theta. So I'm going to give you a worksheet with 5 more polar curves, okay? And on those polar curves, there's a couple things that I want you to do. Number 1, let me write down the things I want you to do as soon as I give you. So to do, the very first thing is, after you open up Desmos, I want you to change using your wrench or your settings. I want you to change your settings. Make sure 2 things are happening. Number 1, you are measuring everything in terms of radians, okay? So make sure you go there and make sure your angles and everything are being measured in radians. And number 2, I want to make sure that you have polar paper. So you want to choose the polar plane to work with, okay? So you want to choose the polar plane, and you want to make sure your settings are in radians. Once I give you this worksheet with the functions, underneath every function, r equals, undo. So you're going to type these functions in, okay? And underneath every function, you are going to find a restriction for theta. Desmos automatically puts in this restriction for theta. So I want you to make sure that you copy this down. I want to see that restriction, okay? We'll talk about what that means. And then when you go to graph these pictures, whatever they are, make sure you try to graph as rigorously as possible. Okay? So try to be as accurately as you possibly can. Now, if that means on your polar paper you decide to make this 1/2 and make this value 1, you know what I mean? Like, make it just so you have units and you can make it as big as you need or as small as you need to make the pictures come in. But I'm going to give you these curves right now. This works. So we are graphing. So first thing is, you guys went over to your wrench, right? Everybody went up to your wrench and you made it polar paper, and you made sure that you were in radian measure, right? So that you got those nice polar circles going on there. And then you typed in r equals 3 sine of theta. And to get theta, you actually type out the word theta, just like it sounds like. It's very cool how it recognizes it. So 3 sine theta gives you just like you said. And so you should be getting a circle, right? But I want to make sure that you copy down what Desmos gives you right underneath it. So right underneath 3 sine theta, Desmos gives you something. Do you guys see what Desmos is giving you? It's giving, well, not that. Go back, Tina. There. What is it giving you down there? It's giving you the restriction on the variable theta. And so Desmos automatically pulls up this. It automatically puts that in there for you. What do you think that means? 0 is less than theta is less than pi. What do you think that means? What do you think that is? 0 is less than theta is less than pi. Well, you could play with it a little bit and put other numbers in there, right? Pi over 4, pi over 2. You see what I'm saying? Minus pi over 2. Oh. What do you think it's doing? What is it giving us? Guesses? What's it telling me? It's actually telling me in what range of t values or theta values does it take for me to go around this curve one time? Because remember, these curves are periodic, meaning they repeat their behaviors. So from 0 to pi, I go once around that curve. I bet you any money from pi to 2 pi, I also go once around the curve. I bet you any money from 0 to 3 pi, I go twice around. You see what I'm saying, guys? So it tells me when it puts there 0 to pi, it tells me how long it takes to get once around the curve. If I have A, I can put a slider and I can check it. Let me put my A's. I want to go from 0 to pi. And if I move A, and let me just go A. So if I'm tracing A, as I'm tracing from 0 all the way until I get to pi, boom. Do you see that? 1, 2, 3. So when I'm at 3, I'm here. At pi over 3, I'm about 2.5, a little more than 2.5. At pi over 6, I'm about 1.5. So as I'm graphing this and putting my points, I'm looking at my angle and I'm saying about how far am I. At pi over 6, I'm about between 1 and 2, so I'm right here. At pi over 3, I'm in between 2 and 3. At 5 pi over 6, I'm again about 1.5 units out. Do you guys see what I'm saying? So when you're plotting these points, you're using two references, your angle and your radius, okay? And that's what you're putting together to get your values. And this here, this restriction tells me the interval needed to traverse the curve one time. And did you guys get symmetry on that first one? What kind of symmetry? In the horizontal or vertical? In the vertical. Symmetry in the vertical. Good, 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 good. Good, good, good. You guys are going through all of them. And it's really important. Do you see how rigorous I was? I put points in. I made sure it was all connected and everything was good there. So I want the rigor. I want you to pick points. Make sure you're graphing a couple points, okay, for your angles. And get some pictures going here. 2 minus 2 cosine theta. So let me see. Let me turn him off. Let me go 2. R equals 2 minus 2 cosine of theta. What you're going to observe often is that your cosine functions are symmetric in the which axis? In the horizontal or vertical? Cosines are often symmetric on the horizontal because of if you think about what cosines are, but that's okay. So R equals 2 minus cosine theta. So this guy at pi over 2 is right here, and at negative pi over 2 is right here. It comes here, and so when I'm at pi over 3, I'm at 1. So pi over 3 is at 1, and so it comes out like this, and down here at 5 pi over 3, I'm at negative 1, and then it goes all the way over here to 4. 1, 2, 3, 4. It goes over here to 4. And 2 pi over 3 maps to 3. 2 pi over 3 maps to 3, and 5 pi over 6 let me see, 5 pi over 6. Ooh, 5 pi over 6 maps almost to 4, not quite to 4. And so this cardioid looks like a cardioid, like a heart. 4 pi over 3 maps to 3, comes over there. So notice, to graph these points, you can always do the angle and then the radius, right? If you look at your angle and your radius, it can get you those points to help you out. This is a cardioid. It looks like a heart. This one is symmetric in the horizontal. Sines would give you symmetry in the vertical. Most importantly, in order to traverse this entire curve, you have to go 2 pi. 0 to 2 pi traverses the whole curve. If you just mess around and put in pi, you only will get half of your curve for this one. So 0 to 2 pi gives you that whole curve, and that's important. The next one was r equals 2 plus 3 sine of theta. Again, we typed the word theta to get theta. Again, what you want to pay attention to is it takes you an interval of 2 pi to get all the way. Desmos automatically is smart and puts that in there for you. It takes 2 pi to get all the way around this one curve picture that they're showing you. And let's see. When you're here, you're at 1. And then when you're over here, you're at 2 and negative 2. And let me get another value. When I'm at 7 pi over 6, I'm about a half. 7 pi over 6 is about a half. And then when I'm at, a little more than 7 pi over 6, I'm at 1. So this guy is doing this. He's coming down, he's coming up, and he's going like this. And again, when I'm at negative pi over 6, I'm about a half. Negative pi over 6 is about a half. And then I'm coming out. And then how high does he go? He goes up to 5. He goes up to 5 up here. 1, 2, 3, 4, 5. He goes up to 5. And when I'm at pi over 6, I'm about 3.5. So at pi over 6, I'm about 1, 2, 3.5. So I'm about 3.5. And when I'm at pi over 3, I'm a little more than 4 4.25. Pi over 3, I'm a little more than 4.25. So this graph is doing this. And then same thing here. Pi over 6 was about 3.5. Pi over 6. So 5 pi over 6 is about 3.5. And up here at 2 pi over 3, I'm like 4.25. So now we're up here. Do you guys see? You're tracing, right? You're putting plot points in. This is symmetric in the vertical axis. You guys are probably be like, Tina, this is so redundant. Why do I care? It is so important that you understand where these things are coming from and that you're able to relate, because we're going to start saying things like, what is the equation of the tangent line when theta is 5 pi over 6? Okay? So what is the equation of the tangent line? What is going on? Do you guys see what it's so important that you guys are getting some recognition or understanding of how these are all fitting. Let's see. E to the negative 0.01. That is really interesting. R equals E raised to the negative 0.1 theta. It's a spiral. You guys got a spiral? And what's interesting, and I'm not sure exactly why Desmos chooses this specific range. I wish I knew. This one I'm not quite sure myself, but what it shows you is enough of a curve, I guess, to get so many times around. And my guess is it takes you 0 to 12 pi to reach what number on the x-axis or on the horizontal axis, to reach the number 1. So my guess is, and I'm going to make this my 1 value, what it's telling you is that's how long it takes to get to that point. But it's starting out here. Where is it starting at? Do you guys see where it's starting at? E to the 0. Oh, it's like negative infinity. Oh, man. If theta is 0, if theta is 0, then it's 1. Oh, interesting. When theta is 0, I'm graphing 0. No, I'm graphing 1. Oh, I have to think this through. Hang on a second. No. Hang on. Let me think this through. When theta is... Now I understand. I didn't even think this through. Do you guys see what's happening? When theta is 0, I should have e to the 0, which is 1. So I should be graphing the point 1 for my r, 0 for my radius, which is this right here. Oh, God. And then it spirals in. This guy spirals in. Here we go. Okay, I think this is fascinating. You guys might not think this is fast. So I'm at 1, and then it starts spiraling in. So when I'm at pi over 2, I'm about 7/8, I'm going to guess. So when I'm at pi over 2, I'm about 7/8. And then I keep spiraling in. So I'm not quite at a half yet. I keep getting closer. So that's like 3/4 when I'm over here at here. I'm about 3/4 in. Oh, 7/8, 3/4. So it comes and it spirals and it's about 3/4. And when do I get to a half? I don't get to a half till I'm back around here at pi over 4. That's when I'm at a half. So this thing is just slowly getting closer and closer and closer and closer. Now I'm at a half. And then I go around again, and 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 I keep going in, and I keep are you guys with me? We keep spiraling in as it gets bigger and bigger. This sucker, I just want to show you the direction. This curve is going inwards, so I'm going to put some direction on where this curve is going as that value of theta gets bigger and bigger. Okay, alrighty. What about symmetry? Do you guys have no symmetry on this one? There's no symmetry because it's just getting closer and closer on all the sides. One more thing here, Rose curves. R equals cos of 2 theta. Oh my God, where is the time going? What restriction did you guys get on theta? Yeah.
For the cosine value?
Yep, for the cosine. 2 pi?
2 pi.
And what restriction did you guys get for the sine value? Zero to pi. Is that because every time I have a sine involved here, I only go 0 to pi? And a cosine, I go 0 to 2 pi? Is that what's happening? What's happening? Well, let's see. Cosine of 2 pi. What is it? Cosine of 2 theta. What is that picture? What did you guys get for that picture? You got, what is it? It looks like a rose, doesn't it? Well, not really. It looks like a flower. It looks like a flower. And it does this. It comes up, and then it goes like this, and then it goes like this, and then it goes like this. And I'm graphing the wrong color because the cosine, the r equals cosine is my green function. So that's my green function, not my red function. But you guys are getting this. Now, 0 to 2 pi means that it takes 0 to 2 pi to get all the way around. What if I change it to pi? Oh, I'm not all the way around, am I? Do you guys see what I'm saying here? 2 pi is necessary to make it go all the way around, okay? What if I change it so I'm cosine of 3 theta instead of cosine of 2 theta? r equals cosine of 3 theta. Now what do I got? And what happened? What did Desmos do? It did what? It changed it to be the restriction. Now changes, are you with me, to 0 to pi, which means it takes me pi units to get around these three curves. Am I making sense a little bit? And how many petals do I have when 3's involved? How many petals do I have? I have what? How many petals? I have 3 petals. Do you guys see that? Whereas when I had 2 theta, I had how many petals? I had 4 petals, so to speak. Are you kind of seeing something that happens? What happens if I have r equals cosine of 5 theta? How long does it take to get around that curve? And how many petals do you expect to have? Do you see what I'm asking here? So if I have 5 theta, how many petals do I have? And how long does it take to get through there? If I have 6 theta, how many petals do I have? And how long does it take to get all of those petals? Notice, you should notice that when you have even numbers inside, the petals double. Are you with me? But the range that it takes to get there changes. Are you all with me? Do you see how long it takes to get around them? Does that make sense? Do you guys see that? So on your homeworks, you're going to have a question about r equals sine n theta, and they ask you questions about how many petals and what's the range and things like that. Okay, alrighty. You guys, how are we? How's everybody? Oh, I didn't graph r equals sine 3 theta, but r equals sine 3 theta looks just like r equals cosine 3 theta, except it's in the wrong spot. It should be symmetric with the vertical axis as opposed to the horizontal axis. So r equals sine 3 theta is giving me a picture that is doing something like this, where it's symmetric with 3 petals. So it goes 3 petals. If I want to make it bigger, I just change the number that's in front, and I see that everybody's done. And we are ready to do calculus. And we are going to take this cardioid, and I want to know what is the equation of the tangent line to this curve, r equals -1 plus sine of theta. I want to know what is the equation of the tangent line to the curve at theta equals pi. So we got a cardioid. We know what it looks like, and we are looking for the equation of the tangent line at theta equals pi. We are ready to put some calculus to our polar curve exploration. Thank you. So when we talk about a tangent line, we first start with the equation of a line. So like it's either y equals mx plus b or y minus y1 equals m times x minus x1. So the good news is, even when you're in polar curves, tangent lines are always written in rectangular coordinates. So we're familiar with these, right? Y minus y1 equals m times x minus x1. Okay, good. Good. So we need 2 things. What do we need? We need a slope, and we need a point. Alrighty. Who wants, what do you guys want to get first? So we need a slope, and we need a point. Which one do you guys want to get first? Slope? Slope. Zach says slope. Let's get slope. Okay. What is slope? Calculus 1. What is the slope of a tangent line? What is that equivalent to? What's our calculus concept? It's the derivative. Thank you, Ben. Specifically, if we're doing x's and y's, how can we write the derivative? It is the derivative of, with x's and y's, it would be the derivative of y with respect to x. Now, I don't have x's and y's, do I? But I do know something about a conversion relationship that gets me x's and y's from r's and thetas, right? What was that? Maddie, you want to have, what was x equals what? X equals what? X equals R cosine theta. X equals R cosine theta. Okay, so Acacia, are you with me? Okay, so what is our R equation? What is our R expression? R is a function of theta, but where is R? It's
That's the -1 plus sine theta.
so X for our equation really is -1 plus sine theta. So X could be rewritten as R cosine theta, which is just -1 plus sine theta times cosine theta. Is everybody okay with that? Do you guys see that? All right, Kevin, are you ready? You're giving me Y. Y is what?
Y equals R sine theta.
Is R sine theta, and so how could I rewrite that? That's equal to,
Or -1 plus sine times sine theta.
absolutely, it's -1 plus sine theta times sine theta. Where have I seen, notice, okay, let me slow down, hang on. Mathematicians, guys, you're in your mathematician brain. X is a function of what variable, Chris? X is a function of what variable? Theta, beautiful. Y is a function of what variable? Theta. So X and Y are functions of the same variable, theta. Where have I seen X a function of something, Y a function of something? What do we call those curves? We just did them. Parametric, right? Except we had functions not of theta, but of, what was our parametric curves often in? What letter? T, right? Do you guys remember doing parametric curves with T's? Am I hitting something right? Didn't we just do parametric curves with T's? X is a function of T, Y was a function of T. Do you guys remember that? Okay, these are actually parametric curves. And what's my parameter? Derek? Theta. So these are parametric curves. Now, why do I tell you that? Because I'm taking knowledge from our past and putting it into what we're learning right now. These are simply parametric curves with a parameter of theta. Okay, now why does that help us? Because we just spent a week doing derivatives with parametric curves. dy dx. All right, Hunter, what was dy dx? Do you remember when our variable was t? What was it? It was...
dy dt over dx.
Exactly, it was dy dt over dx dt. So Ethan, we're expanding our knowledge, right? Instead of t, our new parameter now is theta. So what do you think the slope is going to be? It's going to be what? dy
over d theta.
dy d theta over
dx
dx d theta. Exactly. So we are simply taking what we just spent a week learning, right? So there's nothing new except we're replacing t with theta. So that means that to get dy dx, we have to take dy d theta over dx d theta. Okay, now the only thing that gets tricky, and I will say what gets tricky, what kind of functions, what's going on in my functions? What do I have in each of those functions? James, I have what going on? I have multiplication. I have a product going on. So when I go to take my derivative of x with respect to theta, what kind of rule do I need there, Hannah? If I have a multiplication, I need what rule for derivatives? I need the product rule. And Dylan, what was the product rule for derivatives? Derivative of the first times the second plus the derivative of the second times the first. Do you guys see past knowledge coming back up again? Do you see what we're bringing up from the back of our brains? We have, yes sir, a product.
So I can't distribute it.
You can distribute it. Now, if you do, now you're going to have to take the derivative of this, which is good. You could do that. You have to be careful because that's a composition. So you would have to use a chain rule. You would have to, which is okay. Are you with me? You bring the chain rule down. So you bring the 2 in front. Do you see what I'm saying, Zach? So you'd have to apply a chain rule. So anybody that decides they want to multiply through and then find the derivative, you are welcome to do that. If you want to do that, but then you'll need the chain rule when you're finding your derivative, and that's perfectly good, and you're going to see you get the same answer that I do. Everybody, so I'm just going to put a little note here. Let me just summarize what Hannah told me and James told me and Dylan told me, is that we have a product, and therefore, because we're taking a derivative, we need the product rule for derivative, which says derivative of the first times the second plus derivative of the second times the first. Or, if Zach says if we multiply it out first, if we so decide to instead multiply it out, then we have to be wary of using a chain rule when we take out our derivative. Okay? So either one works. So we can either use the product rule or we can use the chain rule. We just have to be wary when we go to do the stuff to use the exact things that are necessary to get us the correct first derivatives. Okay, so let's see. So I'm coming down here and we're doing our slope, which is dy dx, which is dy d theta over dx d theta. We are getting this tangent line before class ends. I'm telling you, we are 1,000% getting this tangent line. Here we go. Dy d theta is derivative of the first, derivative of sine is cosine, times the second, plus the derivative of the second times the first. And then I'm doing it with the dx d theta and making sure everybody's getting what I'm getting. Derivative of the first times the second plus the derivative of the second. Wait, I'm doing the wrong function. Hang on. Derivative of cosine is negative sine. Derivative of, and then negative 1 plus sine. Okay. Whew. I almost had that all wrong. So let me see what I got when I simplify this down. That way I know if I'm matching what you get, okay, Zach? So dang it, Tina, erase that whole try this again. Dy d theta over dx d theta is, let's see, so we've got on top cosine of theta, sine of theta, plus, minus cosine of theta, minus plus cosine of theta, sine of theta. Oh, I'm actually getting 2 cosine theta, sine theta on top. If you so choose, you don't have to, but if you so choose, I'm doing this so that I match what you get, Zach, if you decided to use your chain rule. And then on the bottom, I think I have cosine squared minus sine theta minus sine squared theta. And some of you might recognize that that's a double angle, but that's okay if you don't recognize that. So I have cosine squared of theta minus sine theta minus sine squared. And if you guys happen to do it a different way, you might have slightly different answer because cosine squared minus sine squared is actually cosine of 2 theta, which could also be 1 minus 2 sine squared. Yeah, did I mess up? Oh, I messed up somewhere, huh? Where did I mess up?
Shouldn't the sine theta be positive?
Oh, yeah, help me out here. Oh, yeah, it should be positive. Was that what you were going to say, Hunter? Thank you. Negative times a negative gives me a positive. Oh, yeah. Okay, good. Guys, don't copy what I did. Fix that on the bottom if you're doing that. Okay, so we have dy dx. Are you guys okay? Are you guys all getting the same match in me? Now, we specifically want dy dx at what point? At what point? When theta is pi. So we specifically want to evaluate this, dy dx, when theta equals pi. So that means I just want to plug pi everywhere in for theta, right? So that gives me 2 cosine of pi, sine of pi. Oh, that is so nice. Because cosine of pi is just what? 0. Absolutely it is. Cosine of pi is just 0. So that drops that whole term out. Drops that term out. Drops that term out. So that's just the negative cosine of pi over cosine squared of pi Are you guys getting that your slope is 1? So I'm getting that my slope is 1. So I know what my slope is. Now I need my point, right? Now I need my point, James.
Sorry, I was pointing.
Yeah, oh yeah, I like my point. Absolutely. Where's my point? Do I have my x and y? What is x? What is y? Where is x? Where is y? Where is x? Max, help me out here. Oh, Ethan, do you see x and y? Do you see an x and a y? X equals something. James.
X equals 1.
Let me see. I'm going to check it and see. Let me see. X equals this. Y equals this, right? You guys see x and y. So you already have x and y. Let's color it pink. Well, pink is too much like that. Green, bright green. X and y's are right here, right? X and y. So that means if I want to get my x value, x is -1 plus sine. And what's my theta? My theta's pi. So that means x is -1 plus 0 times -1, which is just -1 times -1. And James, you are correct. I get x is 1. So when theta is pi, x is 1. Ooh, I need a different color because that's not showing up on the board. So let's do y equals -1 plus sine of pi times the sine of pi. Oh, hello, sine of pi is just 0. So that's just y equals 0. So now I have my x value and my y value. And so that tells me that I have the equation of the tangent line. Not only does it tell me the equation of a tangent line, but it tells me the point on my curve where this is happening. Theta is pi. When theta is pi, I am actually right here on my curve at 1 for x, 0 for y. And when I draw that equation for that tangent line, y equals x minus 1, do you see where I'm at, right? X is 1, y is 0, right here. And this is the tangent line to this curve right there. What do you think? It all fits, doesn't it? Do you see it? It does. It does. It all fits. It's so cool. All right, when you come in on Wednesday, we're going to do more parametric, we're going to take more tangent lines to polar curves, and then we're also going to start talking about area, integration. So then we'll pull integration in. How much area is inside a cardioid? You see what I'm saying? So cool stuff. I'll see everybody Wednesday. I'm going to my office for office hours.